So we start with what is called the spatial Durbin model, which ever since about the last definitely 15 years or so is like the go-to model in empirical work in spatial econometrics or spatial regression analysis. Not always for the right reason, as I'll mention in the discussion. So the origins of the spatial Durbin model and the reason it's called that are in a time series counterpart. In time series, it turns out that you can estimate a model with a spatial autoregressive error term, serially autocorrelated error term, as a standard regression with a serially time-wise lagged dependent variable. So you have the counterpart of our spatial model, but then this would be not WU, but UT minus 1. This would be UT. This is YT. Then it turns out you can estimate this parameter lambda in a regression that includes YT minus 1 on the right-hand side. In space, you can't do that. Well, no, let me qualify this. An least squares regression of y on the yt minus 1 and the x variables. In space, you can't do that because the least squares regression, as we've seen, yields endogenous, is biased because the spatially lag dependent variable, so the wy, is endogenous. And so the shortcut, and that was a Durbin shortcut, you know, this is old, really old, when people were doing things with, you know, calculators and not by computers. So they were looking for ways to simplify the estimation. That's where this comes from. Now, in space, there's a similar conceptual framework, but no least squares. Okay, so what is a conceptual framework? We start with a spatial autoregressive error model. So that means the vector, all observations of the error term, you don't see the error term. This is not the residual. This is a mathematical construct, right? This is how randomness enters into your regression specification. Is a function of the spatially lagged error terms. In other words, these, for each observation, these are the average error terms in the neighboring locations, plus an innovation. Okay. And this is the same as what we've seen the other day, where we had y, rho, wy, plus x beta. So this structure here is the spatial autoregressive structure, right? And then we have a standard regression. So that was the second classic model that we saw the other day. The first one was the lag model, where we have rho wy as an added term. The second was spatially correlated errors, either autoregressive or moving average, right? This is autoregressive only. So we can solve this, quote unquote, just like we did before in a reduced form, but this is not a usable reduced form other than for mathematical purposes, because you can't observe any of this. You know, the error term U or the error term E is not observed, but you can still write mathematically that U follows from this nonlinear transformation, nonlinear in the coefficient, of the original errors. And what we saw with the simulations the other day is that you generate these errors, say standard normal, then you apply this transformation to it, and then you end up with spatial autoregressive error terms that you plug into the standard regression specification, and then in a simulation that gives you spatially correlated dependent variables. So those are the mechanics. Now, if you do a little bit of matrix algebra, you plug this, we are back to this specification now. We're going to replace U by its solution here, right? That gives us this expression. Now, this expression has a big inverse in it. How do we get rid of the inverse? By pre-multiplying by I minus lambda W. So we pre-multiply left, we pre-multiply right, and we pre-multiply the error term, which gets rid of the inverse term, and we are with a standard regression. A standard regression, but one, if we knew what lambda was, this would be very easy to do. This expression here is y minus lambda wy. So that's the original observation minus lambda times the average of the neighboring observations for y. This is called a spatial filter. Don't ask me why, that's what it's called, because in a sense, you can think of it as filtering out the effect of the neighbors. So you subtract the effect of the neighbors. This is similar, but not the same as first differencing in time series. So in time series, you do a first difference to get rid of cross-sectional effects. Here you can't do first difference because the value of lambda equal 1 is not allowed. So we always have to estimate lambda. We cannot estimate it with least squares, so we don't really gain anything other than some insight that we can rewrite a spatial autoregressive error model in this form. So we write it as two spatially filtered variables. If we knew what lambda was, then we can do straight regression. This is called spatially weighted least squares. We'll see that in a couple of weeks as one of the ways of estimating a spatial error model. The end result is always spatially weighted least squares. As it turns out, as long as you have a consistent estimate for this lambda, you're in business. And then we'll see how do we get this consistent estimate, later. That's how we're going to operate. So this is nothing but an equivalent formulation. Either you write this with two equations, or you write it in the spatially filtered form as one equation. Now, if we work out this form, we move this part over here, then we get what I call a classic spatial Durbin specification, which is, ironically, a spatial lag model. So the spatially autoregressive error model turns out to have an equivalent form as a spatial lag model, but there are constraints on the parameters. If you look at this very carefully, because this comes from this spatial filtering expression here, we have to respect that the autoregressive coefficient, here called lambda, and each of the betas multiplied together and made negative should equal each of the coefficients of the Wx variables. So Wx are the spatially lagged explanatory variables, just like an SLX model, but they are weighted. They're not just gamma, as we saw before in the SLX model, but it's lambda times beta. And this beta is the same as this beta, and this lambda is the same as this lambda. This is called a common factor constraint. And in the old days, in time series, this was used to figure out what the proper decay lag length was, but in space, it's not useful for that, and definitely not nowadays. Okay, so this is all good and well. Two little details that are often forgotten. One is that you cannot do a spatially lag of the constant term. Why not? what is the average of the values of the constant term in the neighboring locations? Constant term is 1, right? They're all 1. So their average is 1. So you're creating perfect multicollinearity. If you would do this, then this first column and this first column would be exactly the same. So the thing would blow up, right? So you cannot do the Wx to the constant term. As a result of that, the constant in this expression, so the first beta, so to speak, is actually a combination of lambda and a true beta. So these are not separately identified. We don't really care. We can identify the product. It's just a constant term. It's not a big deal. But these are two things to keep in mind in this model. So far, so good. We have a model with a nonlinear constraint, actually not one, but one for each regression coefficient, except a constant term. For each regression, for each slope coefficient, if you wish, there is this nonlinear constraint. And that's called the common factor hypothesis or common factor constraint. If there are k explanatory variables, including the constant, then there are k minus 1 such constraints. For each of the beta, this product must hold. So the product of the autoregressive coefficient with each individual beta has to equal the coefficient of the Wx, the corresponding Wx variable. So this is written out in long form. The negative of the coefficient of the spatial lag term type each regression coefficient of x equals the coefficient of the matching spatially lagged explanatory variable. And you can test this, and we'll see later we're going to test this.
So this lambda dot beta.
This?
Yeah.
This is the product of the individual. So it's confusing because these are all different parameters, but this constraint needs to hold. So the product of this lambda times each beta has to equal whatever the matching coefficient is of Wx. So if X is a constant term, income, unemployment, Wx is going to be the spatial lag of income and the spatial lag of unemployment. Then your autoregressive coefficient times the coefficient of income, negative, has to equal the coefficient of the spatial lag of income. That's a nonlinear constraint on the coefficient. So the product, if you estimate this without imposing the constraint, that is a spatial lag model with an X and a Wx, okay? Then you can check whether what you find here, let's say you find 0.2, right? And here you find 10 as the beta. What should this be? Minus 0.2 times 10, right? It's 2. So that is satisfying the common factor constraint. Okay. Of course, if you do this in practice, since each of these estimates has a random component, that's never going to hold exactly. The question is, does it hold enough? And that's a test on the common factor hypothesis that we'll see later. Okay. So this is the common factor constraint. If this constraint holds, then these two expressions, this spatial lag expression and this spatial error expression, are exactly equivalent. They're the same thing. So this, the first one, is a classic expression of a spatial error model. This one is the expression of a spatial lag model, but a complicated one. If these constraints hold, then these two are exactly the same. This is important. As we'll see in a few minutes, this spatial autoregressive specification implies a spatial multiplier effect, in that the changes in one location spill over into neighboring locations. The spatial error model doesn't have that, because on average, the errors are zero. So whatever effect happens in the errors gets washed out. You don't have to worry about it. Right? So if, in fact, we estimate a model like this and the constraint holds, but we don't pay attention and we estimate a bunch of spillover effects, we're mistaken. With an error model, there are no spillover effects because they're all in the error term, they wash out.
So what is the implication of lambda here?
I'll get to that in a second. The implication is this. If you estimate an unconstrained model, and this model became very popular actually about 10 years ago. There was an editorial that says, this is the new way, raising the bar, it was called. So we have a new model instead of the old spatial lag model, which was just WY and X. Now we also include WX. And the rationale was WY gets the endogenous spatial effects, WX gets the exogenous spatial effects. So this has got to be superior to a model that only includes the endogenous spatial effects. Now, why is this not quite correct? Think about what we said about the spatial lag model. It's a simultaneous model. You don't actually observe the average of the neighboring Y because I am my neighbor's neighbor. If I influence the Y at the neighboring location, then that neighboring location influences my dependent variable. So it's a system with simultaneity, with feedbacks, and we got to get rid of these feedbacks by using the reduced form. And once we get the reduced form, what's on the right-hand side? X, WX, and higher powers of W times X. So actually, the spatial lag model already has WX. Now, there's nothing wrong with adding another WX as long as you know what you're doing. This is not a pure WX in a sense. This is a WX on top of the WX you already get from the reduced form. So the reduced form in this model, which is called the unconstrained spatial Durbin model, will be more complex than the reduced form in the standard lag model, as we'll see in a few minutes. So if the common factor hypothesis is rejected, then we're free to interpret this any way we want. But if it's not rejected, in other words, if we can't find any evidence that this constraint doesn't hold, then the real model is an error model and not this complicated form. And again, the main implication of that is in the interpretation. Okay? The unconstrained spatial Durbin model will have a fairly complex interpretation in terms of impacts and spatial spillovers, direct and indirect effects, as we'll see in a few minutes. The spatial error model has none of that. There's no spillovers. It's all in the error term, it washes out. Here's the reduced form. This is what I'm talking about. So in the spatial lag model, the one we saw last time, the reduced form is just this first part, what is here gamma 2, we call beta. The second part wasn't there, and then the error term. And the error term is also pre-multiplied by this, but it doesn't really matter for our purposes. So what's different here is that the reduced form in this first part already has Wx, and then the second part has Wx again. So the coefficient of Wx in the reduced form is actually gamma 1 times gamma 2, which is really the autoregressive coefficient times the beta, plus the gamma 3, which is the coefficient of Wx. In the pure lag model, it's gamma 1 times gamma 2, or we call that rho times beta. In the SLX model, it's just gamma. No, it's not, no beta involved, no rho involved, just gamma. So it's important to keep in mind, there's nothing wrong with the spatial Durbin model. There is something wrong with the interpretation. First of all, it's not true that there are two separate effects, a pure endogenous effect and a pure exogenous effect. The endogenous effect already has an exogenous effect in it because of the reduced form. And secondly, the interpretation of the spillovers, as we'll see later, is more complex because you have two parts to it. You have the first part, which we called rho times beta, and then you have a second part, which is the coefficients of the corresponding Wx. So there's a greater effect of the immediate neighbors. In the spatial lag model, the effect of the immediate neighbors, that's Wx, is rho times beta. In the spatial Durbin model, it's rho times beta plus gamma. Okay. Now, why is this important? You may say, well, it's just a mathematical thing. Doesn't really matter. It matters at one level, and I have a lot of discussion with people about this. So from my perspective, a model needs to make sense. And in my book, a model that gives more weight to a variable in the neighboring locations than to the same variable in the focal location doesn't make any sense. That is an explosive process. If your neighbors have more influence on you than you do yourself, from my perspective, unless you have a really good theoretical explanation, that doesn't make any sense. If I go with Tobler's law, everything depends on everything else, but closer things more so, that means that further things depend less, right? That's the flip of the Tobler's law. So there is no way, according to Tobler's law, that the neighbors have more influence than the focal point does, or for that matter, the neighbors of the neighbors. So in a strict mathematical way, you just get whatever estimates you get. From my perspective, it's important to make sure that this, which is really in our other notation, rho times beta plus gamma, is not larger than beta. Now, rho times beta will never be larger than beta because rho is always less than 1. So we're good. Tobler's law is always satisfied in the spatial lag model. But in the spatial Durbin model, because we throw in this additional neighboring effect, we have to be careful that we don't give too much effect to the neighbors. Because at least from Tobler's perspective, Tobler's law perspective, that doesn't make sense. Now, if you have a good reason why it would make sense, it's fine with me. But by and large, it doesn't. By and large, there's no good reason that your neighbors, for example, your neighbor's house characteristics should be more important to determine your house characteristic than your house is. To me, that doesn't make any sense. Now, there may be contexts where that makes sense. I'm not excluding it. All I'm saying is pay attention to the numbers that you get. Because the data don't always respect this model that you force on them. And if you get numbers, just like what I mentioned the other day with the nonlinear SLX, if you get coefficient estimates that imply an immediate cutoff, basically what they are saying is there is no effect of the neighbors. Right? Even though you have a nice model with the SLX terms in it, when you get your coefficients, these SLX terms don't matter. That's what that means. Even though they may be significant in a statistical sense, in a substantive sense, they don't make sense. So here you can get significant coefficients in a statistical sense that just has to do with the standard errors of the estimation. But in a substantive sense, if you get numbers that suggest that the effect of the neighbors is larger than the effect in place, think twice. That's all I'm saying. Okay, that's the spatial Durbin. If you miss the spatial Durbin, we see a similar phenomenon that we saw with the spatial lag model, only worse. Okay, these move out and standard error gets larger. And so it's basically an omitted variable problem, which is worse than in the lag case because you're omitting two things, right? Two additional terms. So that's the spatial Durbin model. I would say 60+% of empirical applications in spatial econometrics use the spatial Durbin model. Do they always use it for a good reason? Not necessarily so. Okay. Then there is what I call the monster. I call it a monster because it does everything. But actually, you can't estimate it. I mean, you can, and you get numbers, but the coefficients of this model are not separately identified. So you get numbers, but they're very difficult to interpret. In fact, some estimation methods won't get any numbers at all. They just blow up, as maybe we'll see later on in a quarter. But so this is a framework suggested by Elhorst, where basically he throws everything together. So we have an unconstrained spatial Durbin model, constant term, spatially lag-dependent variable, exogenous explanatory variables, spatially lagged exogenous explanatory variables, and then on top of that, we get a spatial autoregressive error model for the error, spatial autoregressive model for the errors. It's very nice as a framework because it shows very nicely how all these different models kind of are interconnected. It's a little bit misleading to call it a nesting situation because in some cases, especially the one we just saw with the common factor hypothesis, they're actually not nested. Okay. But as a framework to think about it, it's very nice because you can then think of specific models as following from this general specification by having particular parameter constraints. So if the error autoregressive coefficient is 0 and the coefficients of Wx are 0, then we have a spatial lag model. If the autoregressive coefficient is 0 and the coefficients of Wx are 0, then we have a spatial error model with the common factor also. If we have both autoregressive coefficients 0, then we have an SLX model. Okay. The problem is that as a strategy to find a specification, so the strategy, and we'll talk about that in the winter in more detail, the strategy would be something similar to backwards stepwise regression. So, you know, forward stepwise regression, you start with a model and then you keep adding additional variables. Backward stepwise regression, you start with the kitchen sink and you start dropping variables, right? So you would estimate this general nesting model and then check. Is rho 0? Is lambda 0? Is gamma 0? And if they're not significant, which means for all practical purposes they're 0, you drop them. And then you go down in the ladder and you start with the big model and you get simpler and simpler models. And then you stop where everything is significant. The problem with that is with the identification, separate identification of the parameters in the general nesting model. And in a very recent paper, Coley and Berra showed in a maximum likelihood framework why that identification problem is there. And this has important repercussions for specification searches. And they call it the 2 out of 3 problem. In that for all practical purposes, you can address 2 types of misspecifications, but not all 3. So ideally, we'd want to be able to check whether rho is 0, lambda is 0, and gamma is 0. And that's not possible. So you have to pick your strategy. You either go with rho and lambda, that's the oldest strategy, or you go with rho and gamma, that's a spatial Durbin strategy. But you can't do all 3. And they call this the 2 out of 3 problem. And there's always been a lot of suspicion, in part because the estimation doesn't work very well. You get numbers, but they don't make any sense. And what you do tend to get is that rho and lambda kind of bump around. So you get a small rho, then you get a big lambda, and then vice versa. And it's very hard to know which is which. But this is a formal proof that it doesn't hold. So as a practical strategy, it doesn't really work to start with the GNS model because you can't meaningfully estimate the GNS model. So Elhorst has this nice little scheme where he shows all the different parameter constraints and how the simpler models follow from the more complex models. I actually follow a different terminology. I specifically don't agree with the SDEM model, which is the spatial Durbin error model. I call this an SLX error model. To me, spatial Durbin requires both the lag of y and the lag of x, and this one only has the lag of x, which is an SLX model. So there's a lot of confusion about the terminology in the literature. I mean, as I told you, people were very enamored with the spatial Durbin thing, so everything becomes spatial Durbin. And the Durbin variables, these are WX. I have no idea where this Durbin thing comes from because they've been around since the early 90s as WX, right? So if you read papers, you'll see this kind of confusing terminology. The solution is always go back to the mathematical formulation. There you see it. What does it have? This one has everything, as we know. This one here has the autoregressive coefficient, WY, and the error autoregressive coefficient. So he calls this SAC. In the literature, this has been called SAR-SAR or SAR error, but not SAC. SDM is spatial Durbin model. We just saw spatial lag of y and spatial lag of x. SDEM has a spatial lag of x and a spatially autoregressive error term. So I call that SLX error model. And then these are 2 parameters. So this is a 3 parameter. Keep in mind that gamma is not 1 parameter, but actually 1 for each WX. So I just call it 3 parameters, but it's really 3 groups of parameters. These 3 models are 2 parameter models. And then these 3 models are 1 parameter model. These are the ones we saw last time, the autoregressive, the lag model, the SLX model, just WX, and the error model, just an autoregressive process. And then the 0 parameter model, of course, is the standard regression. So in a specification search, you can go, sorry, it's a little bit too sensitive. In a specification search, if you could estimate this model, you could go this direction, but you can't, so you have to start somewhere here. Or you can go this direction. And what we'll see next week is how to go this direction for these kinds of alternatives. So what is the problem with some of these hypothesis tests? The common factor hypothesis and the fact these are not clearly nested models. They're somewhat nested. But it's a nice framework for you to keep track of the different ways in which you can bring spatial effects in a regression specification. You can do it with one parameter, the 3 simple models, lag, error, SLX. 2 parameters, spatial Durbin, SAR, SLX error. 3 parameters, GNS.